Okay, so my project is on bioengineered tissue construct for knee meniscus repair. So we know that the meniscus are these C-shaped fibrocartilaginous structures in the knee, and they're responsible for carrying the majority of the load. So a healthy meniscus is really important for functioning of the knee joint in general and to protect the underlying cartilage. In fact, meniscus damage is a precursor to OA, and also meniscus tears are the most common type of traumatic knee injury. So clearly this is a clinical problem, and treatment options that are available right now have high midterm failure rates, and secondary OA is common. And in the worst case scenario, joint replacement surgery is necessary. So there's a clinical need to provide a new solution that offers long-term advantages to the patient. And our goal is to develop this new long-lasting treatment strategy for defect repair using a functional tissue engineering approach. So we've developed what we call a bottom-up, iterative, computationally assisted method to designing a construct. So any computer model is dependent on robust input. So what we first need to do is characterize the tissue to develop structure-function relations for human meniscus tissue. And then from that, we can develop our new computational model and identify what are the critical structural and functional parameters that should be included in the design. We can then design a construct and virtually assess its functionality using our computer model. We then ask ourselves, does this construct recapitulate human tissue? If the answer is no, we can then use our model to identify what are the critical parameters that we need to fine-tune and start the process again until we get an answer of yes, in which case we can move to the benchtop and do cell seeding in our ex vivo model. So as I mentioned, the first step is tissue characterization. So we want to look at mechanical, electrochemical, and transport properties, of which there's very little quantitative information in the literature right now. Once we have that information, we can build our computational model, which will be based on mechano-electrochemical mixture theory. So the important thing about this model is we can look at different scaffold design parameters and see how does each parameter contribute to the functionality of the scaffold, and if we change one, what happens? And we can assess that virtually. Once we're happy with our design, we move to the benchtop, like I said, and we'll make a construct using electrospun fibers that are derived from decellularized meniscus. So we'll build our scaffold, assess it, see if we like what we're seeing, if not, redesign it again. Once we're happy, we can seed cells and then put it in our ex vivo defect model. And at each step, we want to compare this with a commercially available system, and we think that we'll be able to provide better results. So at each step in our process, we have significant scientific and translational outcomes, which include this new gold standard set of data that can be used to design new constructs and a new tool. And most importantly, we believe that with this system, we'll be able to achieve better integration and regeneration of the meniscus, and which will in turn lead to reduced OA in the knee. Thank you.